So in the previous lecture, we have defined dead load, superimposed dead load and live load as a load pattern. After that, we need to define seismic loading. Before we define seismic loading, we need to be clear about the Indian Standard Code about the earthquakes. So I want to give you a brief reading of what exactly our Indian Standard for Earthquake guide us for the buildings. Otherwise, it will be difficult for you to understand what exactly we are doing. So this is the Indian Standard for Earthquake 1893 Part 1, which was released in 2016. In this, first of all, is the definition of closely spaced modes. What is meant by critical damping? That is a damping beyond which free vibration motion will not be oscillatory. Damping, which is a very important parameter, that is the effect of internal friction, inelasticity of materials, slipping, sliding, etc. in reducing the amplitude of oscillation. Design acceleration spectrum, it is also a very important parameter. It refers to an average smoothened graph of maximum acceleration as a function of natural frequency or natural period of oscillation for a specified damping ratio for the expected earthquake excitations at the base of a single degree of freedom system. After that, design horizontal acceleration coefficient AH. Design horizontal force ductility, it is the capacity of structure to undergo large inelastic deformations. I have already covered the definition of ductility in my previous lectures. Epicenter, flow response spectrum, importance factor. Importance factor, the code gives us an importance factor value for different buildings. Intensity, liquefaction, model mass of a structure, mass model participation factor. So the amount by which natural mode K contributes to overall oscillation of structure during horizontal or vertical earthquake ground motion. So natural period, the code gives us a formula for the natural period, fundamental Newton translational natural period. The code gives us a formula. Peak ground acceleration, which we name it as PGA, response reduction factor, I have already covered in my previous lecture. It is the factor by which base shear induced in a structure, if it were to remain elastic, is reduced. I repeat, reduced to obtain the design base shear. So basically, as I told you earlier also, we do not design the structure for full earthquake. We design the structure for earthquake divided by the response reduction factor. That response reduction factor, why we are providing? Because of the ductility of the structure. Response spectrum definition, response acceleration coefficient SA by G, seismic mass, seismic weight, seismic zone factor. Basically, a country is divided into various zone factors. There are zone 2, zone 3, zone 4 and zone 5. A simple definition of time history analysis. Base. What is meant by the base as per the Indian standard? It is the level at which inertia forces are considered to transfer to the ground through the foundations. The center of mass, center of resistance, eccentricity. Eccentricity is the value to be used for floor I in calculation of design torsion effects. Design seismic base shear, diaphragm that we had already assigned, height of the floor, height of the building. It is a very important definition of the height of the building. Mostly people are confused whether we should include the basement story height or exclude the basement story height. Basically what is happening here is that the height of the building is from its base to the top of roof level, excluding the height of basement stories if basement walls are connected with the ground floor slab or basement wall are fitted between the building columns, and including the height of basement stories if basement walls are not connected with the ground floor slab and basement walls are not fitted between the building columns. In our case, the basement walls are fitted with the building columns, so we need not consider the height of the basement stories. That is, height of the building shall be from this level to terrace level. Or if we see it in drawing, this is the height of the building for earthquake concentration, that is 92.8 meter. After that, the code gives us guideline for horizontal bracing system, joints, lateral force resisting system, moment resisting frame. There are two types of frames, that is ordinary moment resisting frame and special moment resisting frame. So ordinary moment resisting frame can be designed and detailed as per IS 456 or IS 800. IS 456 is for Indian standard for concrete design. IS 800 is for steel design, and not meeting special detailing requirements for as per IS 13920 or IS 800 respectively. But for special moment resisting frame, as we are providing in our building, we are providing SMRF, that is special moment resisting frame in our building, so it has to be compliant with IS 13920. Number of stories, it is the number of level of building above the base at which mass is present in substantive amounts. This excludes the basement stories where basement walls are connected with the ground floor deck or fitted between the building columns, and include the basement stories when they are not so connected. Now, like in high-rise building, core structural walls, perimeter columns, outriggers, and belt truss systems, these four type of structural systems are the most dominant while we are designing very high-rise buildings. Our building is only 26 story, but if we are going for buildings where height is approximately, or the number of stories are more than 50 or number of stories are more than 100, then we need to assign these type of structural system to the building. After that, principal plane axis and P delta effects. In our building, we need to consider P delta effects. How we need to consider that I will tell you later on. RCC structural walls, there are two types of RCC structural walls: ordinary RCC structural walls or special RCC structural walls. Ordinary RCC structural walls need not to be designed as per this IS 13920, that is earthquake detailing standard, and special RCC structural wall has to be designed as per IS 13920. Now there are two type of stories, soft story and weak stories. Both of these stories are prohibited as per the latest standards. Soft story is the one in which lateral stiffness is less than that in the story above. That is when we are considering this ETABS model. For example, if the stiffness flow, then it will be called as a soft story. And weak story is the one in which story lateral strength is less than that in the story above. So there are two types of things, soft story and weak story. Soft story is the one in which lateral stiffness is less than that of story above, and weak story is the one in which the lateral strength is less than that of the story above. After that, you need to be clear about what exactly do you mean by story drift. It is the relative displacement between the floors above or below, not the total deflection. So the story drift will be like if this floor is displacing 10 mm on the right hand side and this floor is displacing 6 mm on the right hand side. So the drift for this story shall be 10 minus 6, that is 4 mm. After that, story shear, it is the sum of design lateral forces at all level above the story I under consideration. After that, story lateral shear strength, story lateral transition stiffness, and RC structural wall plan density. These are the parameters that code has provided us with definition. After that, there are various parameters that code is guiding us, that earthquake will not likely to be occur with high wind or high maximum flood or maximum sea waves. That is, we never mix earthquake loading with the wind loading. After that, load combination, code has guided us, load combination shall be as specified in the respective standard. That is, for they shall be different for concrete and steel. Now this is a very important part, that is clause 6.3.2, design horizontal earthquake load. When the lateral load resisting elements are oriented along two mutually orthogonal horizontal directions, structure shall be designed for effects due to full design earthquake load in one horizontal direction at a time and not in both directions simultaneously. That is, when the building is perpendicular to x and y axis or parallel to x and y axis, then that building shall not be checked for the combined this type of loading, that is ELX plus 0.3 ELY. When the building is not perpendicular to the, or like the building with a very special structural shapes, then that building need to be designed for ELX plus 0.3 ELY plus minus and plus minus 0.3 ELX plus minus 0.3 plus ELY. So where x and y are the two orthogonal horizontal plane directions. So this is the load combination that shall be considered for non-orthogonal buildings that I had also enclosed in this Excel file. I have prepared a list for all the load combinations that need to be done when the building is non-orthogonal, and this is the load combinations for the building in which the building is orthogonal to the x and y axis. Here in our case, the building line is parallel to x-axis and building line is parallel to y-axis. If this building must have been rotated like this, so that building is non-orthogonal, and in that case we need to apply this type of loading and design vertical earthquake effects. Now this is a major change in the latest earthquake standard. Whenever a structure is located in seismic zone 4 or seismic zone 5, we need to design the structure for vertical earthquake also. In addition to that, wherever vertical earthquake has to be considered when the structure has vertical or plane irregularities, structure is rested on the soft soil, bridges, structure has long spans, or the structure has large horizontal overhangs or structural members or subsystems. So in our case also, I have prepared this list of load combinations. Here this RSX, RSY and RSZ, that is response spectrum load along X, Y and Z. Z is the vertical axis. So in that case, I had prepared the list that is RSX plus 0.3 RSZ and RSX minus 0.3 RSZ. So I am combining the horizontal response spectrum load cases with the vertical response spectrum case. So this is the guideline, and this type of loading shall be followed where the structure is non-orthogonal in addition to the structure being in seismic zone 4 and zone 5, and all these conditions are satisfied for that. So that the code also allows us to increase the net pressure on soil in design of foundations. So when earthquake forces are included, net bearing pressure can be increased as per table 1. This is the table 1. So when there is rock or hard soils, we can increase the bearing capacity by 50%. When it is resting in medium or stiff soil, we can increase the bearing capacity by 25%. For soft soil, increasing in bearing capacity is not allowed. After that, this is the main formula to calculate a design horizontal seismic coefficient, that is Z by 2 into SA by G divided by R by I. The seismic zone factor, it is given in table 3. That is, the whole country is divided into various standards, zone 2, 3, 4 and 5. In our case, the building is in Delhi, and green color means that it is basically a zone 4. So for zone 4, we need to provide Z value as 0.24. Yeah, before that, importance factor I is 1.5 for critical and lifeline structure, 1.2 for business continuity structures, and 1 for the rest. And R response spectrum factor shall be as per given in IS 1893 part 1 to 5 for the corresponding structures. Like in our case, if we are designing a ductile building, the R shall be 5, and SA by G shall be taken from the response spectrum curve, from this curve. So if we know the natural period of the building, which code gives us formula to calculate, we can calculate the SA by G value. You will notice that there are two response spectrum curves. In the previous code, there was only one response spectrum, but now if we are designing by equivalent static method, the code has instructed us to take the 2.5 SA by G from this point to this point. But if we are doing response spectrum method, we can consider this part. For tall building, time period is somewhat high, so SA by G value usually lie in this range. And for base isolated building or for special buildings, the SA by time period is usually in the range of 2.5 to 3 seconds. So for that building, SA by G value reduces to a very great extent. So in addition to that graph, code has also given us this formula, that is, if time period is in the range of 0.4 to 4 seconds, we can calculate SA by G for rocky or hard soil by 1 upon T, or for medium to stiff soil by 1.36 upon T. And for use in response spectrum, this is given us separately. So there are three types of soil: rock or hard soil, medium soil, or soft soil. The code has also given us definition of what basically do you mean by hard soils, medium soil, or soft soils. For hard soil, well grade GW, HW. For medium soil, MLCL. For soft soil, it is basically MI, MH, CI, CH, or the combinations. So code has also given us basically two methods. Effect of design earthquake loads can be considered in two ways: equivalent static or dynamic analysis method. So for under dynamic analysis, the code has given us three options: response spectrum method, model time history method, and third is time history method. So in this standard equivalent static method, response spectrum method, and time history method are adopted. After that, for structural analysis, moment of inertia code has guided us that 70% of IG for columns, 35% for beams, and steel structure it shall be gross. And this is the case for vertical earthquake, that is AV. The code has guided us that design horizontal spectral value AV for vertical motion shall be taken as 2 upon 3 of whatever we were doing for the horizontal forces. How we will accommodate this or how we will calculate this, that I will tell you in the real example. So code has also given us a definition of irregular building. We were discussing about the non-orthogonal building. This is a non-orthogonal building. And in addition to that, this is a irregular building, that is L shape or this plus shape building. Re-entrant corners we have already studied in our previous lecture. This is a re-entrant corner here, and this is a re-entrant corner here. Stiffness irregularity. The code has this is a very important table number 6. Whenever we are designing a building, we should make sure that all the concepts in this table 6 are followed. So stiffness irregularity, we should check that the structure does not have any soft story. Structure does not have any mass irregularity. The code also gives us the guidelines. If the structure has mass irregularity, then the dynamic analysis method shall be adopted. We cannot go ahead with static analysis method. After that, structure should not have any vertical geometric irregularity. If yes, then we shall estimate the earthquake effects by dynamic analysis method. Strength irregularity, the structure. See, this feature is undesirable and hence should be prohibited if it is a part of supporting the primary lateral load resisting system. Floating or stub columns are always undesirable feature in any kind of building. This is the formula to calculate the static base shear, that is AH into W. AH can be calculated by Z by 2 into I by R into SA by G that we had studied above. This is AH, and W is the seismic weight of the building. So minimum design lateral force shall be calculated by this method. This is the example of vertical geometric irregularity. This type of building is never desirable in high seismic zones. After that, importance factor. Importance factor shall be high for, that is, hospital buildings, television station buildings, bus stand, metro station buildings, railway stations, fire station, large community hall buildings. It shall be 1.5. For residential and commercial building, it shall be 1.2, and for all other buildings, it shall be 1. Plus, in addition to that, code also gives us the freedom to choose the importance factor. We can also go ahead with importance factor of 2, but it will increase the budget of that building. After that, response factor, reduction factor, design imposed load. Yeah, this is also a very important concept, that what exactly shall be the response reduction factor for different building systems. In our building system, this is RCC building with special moment resisting frame. So the response reduction factor is 5. If we are going with braced frame system, that is OBF ordinary braced, SBF special braced, having concentric and eccentric. For eccentric braces only reduction factor can be 5, whereas with concentric braces response reduction factor is 4.5. For structural wall systems, the response reduction factor is 1.5 for unreinforced masonry and all these things. For dual system, that is building with RCC structural walls and ordinary moment resisting frame, it shall be 3. Whereas in our case, the building has tactile RC structural walls and special moment resisting frame, so the response reduction factor can be chosen as 5. For the building having flat slab system, the response reduction factor is 3. In addition to that, for the code is guiding us that for flat slab structural wall system, see note 4. In note 4, it is written that punching shear failure shall be avoided and lateral drift at the roof under design lateral force shall not exceed 0.1%. Please note that this is a very difficult value. Lateral drift at roof shall not exceed 0.1%. This is a very difficult feature to achieve. Usually drift exceed 0.5% to 1% for very high-rise buildings. So that is why code is encouraging us not to go ahead with flat slab system. After this is also a very important part. Here this feature we will use while defining mass source in ETABS. For calculation of design seismic force, the code guides us that if our floor loading is above 3, we can reduce the imposed load by 50% while calculating the earthquake effects. And when it is up to and including 3, we can reduce the loading by 25%. Here snow loading is also there. So code is guiding us that 20% of uniform design snow load or sand load shall be included in the estimation of seismic weight. Now for seismic weight also, it is dead load plus appropriate amount of imposed load. Why it is writing appropriate amount? Because we can reduce the percentage of live load. Now this is a very important part, that how to calculate the fundamental translation natural period. It is different for different types of building. For bare moment resisting frame without any masonry infills, for RCC moment resisting frame building, it is 0.075 into h to the power 0.75. For RCC steel composite moment resisting frame building, it is 0.08 into h to the power 0.75. And similarly for steel moment resisting frame. Whereas there are some buildings which only have RCC structural walls, not even a single column. So for those buildings, we need to consider, or we need to calculate this time period with the help of this formula. That is 0.075 into h to the power 0.75 divided by under root of AW. And all other buildings, that is building having masonry infill walls, we can calculate time period by 0.09 into h upon root t. In our case, I would like to go ahead with this formula. That is for RCC moment resisting frame building without any masonry infills. You will notice that this building does not have any significant masonry infills except for this masonry infill and this masonry infill, that is also being broken by this glazing. So we need to calculate the time period with the help of this formula, that is 0.075 into h to the power 3.4, where h is this height. (92.8 meter). So h is 92.8. So h is 92.8 to the power 0.75. This is approximately 29.89 into 0.075. So the time period of our building is 2.24 seconds in both the directions. So we need to remember this time period, that is 2.242 seconds. We can enter here 2.242 seconds. After that, the code is also guiding us how to distribute the vertical base shear. In this type of building, height is from this point to this point, but in this type of building, as in our case, the height is from this point to this point. The code is also guiding us to calculate different type of heights for different type of building. The code also gives us the definition of diaphragm. The code guides us that diaphragm has to be considered flexible if it deforms, that the maximum lateral displacement measured from the chord of the deformed shape at any point of diaphragm is more than 1.2 times the average displacement of the entire diaphragm. That is, the diaphragm deflects like this. So in our case, it is a RCC slab, so it won't deflect like this. This type of displacement may be negligible in our case. After that, it gives us the guidelines for dynamic analysis method. So under dynamic analysis, this is a very important definition. The design base shear VB estimated shall not be less than the design base shear VB bar calculated using a fundamental period TA. So that is why we need to do the scaling. That is, whatever base shear that we had calculated using the response spectrum and whatever base shear that we had calculated using the static analysis, they both need to be matched. What exactly I mean, we shall do in the ETABS model. Then it will be clear. Number of modes to be considered, we should consider that much amount of modes such that 90% of total seismic mass is participating, and the natural frequency shall not go beyond the 33 Hz. That is, the time period shall not be less than 1 divided by 33. It shall not be less than 0.03. This we will also check in the model. And combination of modes, it is also up to us that whether we want to do the CQC or SRSS, that is sum of root of sum of squares method. We also need to check model participation factor. We also need to check the design eccentricity. By default, it's the 0.05 design eccentricity. This is a guideline where we can model the masonry infill walls. We can model a diagonal strut with width having this value. After that, the code guides us that what shall be the story drift limitation. It also guides us that the distance between two adjacent buildings shall not be less than this. For foundation, it is also giving us this guideline. For compound wall, it is simply guides us that importance factor shall be 1, response protection factor shall be 1, and SA by G shall be 2.5, and design horizontal coefficient AH of 1.25Z. After that, it is also guiding us for vertical projections. For horizontal projections, so this is a map showing epicenter of the earthquakes. This is a map showing principal tectonic feature. So Delhi is sitting on Himalayan tectonic zone. That is why the zone factor is quite high. Similarly, this area is also very critical to the, this area is also zone 5, which is sitting on this frontal folded zone and Himalayan tectonic zone. Sorry, Araham Yoma folding zone. This is a map showing principal lithological features. So this is an lecture where the code is guiding us that what the code has distributed into 12 features. That is, this is the maximum devastation, and this is the not noticeable, that is minimum devastation. After that, the code gives us different values for zone factors for different regions, and this is the guidelines where the code is guiding us how to evaluate the liquefaction potential. In this lecture, we will define the seismic loading along all the directions. So we need to define seismic load along x plus 0.05 eccentricity, x minus 0.05 eccentricity, y plus 0.05 eccentricity, and y minus 0.05 eccentricity. So we go to define load patterns. Here we have already defined dead load, live load, and superimposed dead load. After that, we need to enter ELX, type as seismic, auto data load as IS 1893 2002, left click on add new load. After that, we need to enter ELX plus E, add new load, ELX minus E, and add new load. Similarly, we will add seismic loading along y direction, ELY plus E, and ELY minus E. So now we need to check that what exactly is the input that we are providing here. So left click on modify lateral load. You notice that it has by default check all the boxes. That is wrong. So for ELX, ignoring eccentricity, we will consider bottom story as stalled, response reduction factor as 5. Zone factor is 0.24 for Delhi. Site type is 2, that is medium soil. Importance factor is 1.2. After that, time period is user defined, that we had calculated as 2.242 seconds. Left click on OK. Same shall be done for all the remaining seismic loadings. Now we are doing ELX plus eccentricity, that is 0.05 eccentricity. Story shall be stalled. Zone factor shall be 0.24 and time period shall be 2.242 seconds. Same for minus eccentricity. Now we shall do the same with the y direction. Left click on OK option. Please do cross check whatever you are doing is correct or not. Like I had missed entering the importance factor. Left click on OK option. So now we have defined all the seismic loading here. After that, we need to define the wind loading. That is wind load along different directions. Before we define wind loading, we need to understand what exactly our code is saying about the wind loading criteria. That we will discuss in the next lecture. So until now we have learned how to apply or how to define the seismic loads, super dead load and dead load. Now in this lecture, we will learn how to define the wind loads along x direction and y direction. To start with that, first of all, we should learn what exactly are the options in our ETABS. So to do that, we go to define and load patterns. Here we can enter WLX, that is wind load along the positive x direction. That is along this direction. We can select type as wind and auto lateral load as Indian IS 875 1987. Now there are two methods here. Either we can select Indian IS 875 1987 or we can select the user loads. First of all, I will tell you the advantages and disadvantages of using this wind loads as per the country standards. If we will go with this option and left click on add new load, left click again on modify lateral load. Here you will see that wind load pattern window will open with exposure and pressure coefficient, wind exposure parameters, wind coefficient and exposure heights. All this looks very easy, like we can readily calculate and we can just input the data and ETABS will calculate the load automatically. But it is just like a black box, which I will never recommend you to do that, cause we never know or we never have full control over the loads that will be generated by the ETABS program. Cause for example, if we take the exposure from shell objects option, this option will nullify and we can enter all this data here and ETABS will calculate automatically. But with exposure from shell objects, we have to model a zero property shell on the face of the building. And with this option, that is exposure from the extent of diaphragms, windward and leeward coefficient we have to calculate and we have to enter the data here. So this type of, like all the data is somewhat confusing and not clear to all the practicing structural engineers. So what we can do is that we can have the full control of the loads that will be applied on our model. Because if we are talking about the 100-meter building or a 200-meter building, wind load is always dominating in one or other part of the structure. So what we need to do here is that left click here and then select auto lateral loads as user loads and then click on modify loads. When we left click on modify lateral load after doing this option, you will find that this beautiful table will open. Here it is written X ordinate and Y ordinate. Here it is written Fx, Fy and Mz, and here it is written the diaphragm. So the one advantage of using different diaphragms for different floor is this, that is we can apply different loads on different diaphragms. Now what kind of load we shall apply? We can apply point load and moment on the diaphragm center. And what is the ordinate of that diaphragm center? This is the ordinate of that diaphragm center. As our building is symmetrical, so this value is same for all the floors. Otherwise, if our building is unsymmetrical, this value is different for all the floors. So what we need to do here is that we just need to enter the point load here. Now, how we can calculate this point load? We need to go to our basics. That is, we need to refer our standard IS 875 2015, or we can refer latest NBC, that is National Building Code 2016. For the practicing structural engineers, you must have read all this, but for the students, this might be new to you. So Indian standard states that we need to calculate first of all design wind speed, that is VZ. How we can calculate design wind speed VZ? We can do that by multiplying VB, that is basic wind speed, into K1 into K2 into K3 into K4. K1 is a probability factor, which is 1 for our building. K2 is terrain roughness and height factor, that shall vary as per this table 2. K3 is topography factor, that is 1 for our building, and K4 is importance factor for the cyclonic region. As Delhi is in non-cyclonic zone, so we can go ahead with 1. So KD, KA and KC are also other factors that we will study later. But now K1 is clear, K3 is clear and K4 is clear. K2 we need to enter manually as per the different heights. That is, if the height vary, K2 vary. So we need to enter all the K2 data here as per the table 2 here. We can calculate VZ, and after calculating VZ, we can calculate PZ. That is 0.6 into VZ square. So first of all, we will understand what exactly is K2. K2 depends on the height of the building, that is height Z, and terrain category. So K2 varies as per the terrain category and height. So if we will go above, the K2 value increases, and if we will go down, K2 value decreases. For example, K2 value is maximum for 500 meters and K2 value is minimum for 10 meters. So if we will consider this area, here you will understand that our building is in terrain category 3. So we will refer this, and here you will see that for 10 meters height, the K2 value is 0.91. For 15 meter, it is 0.97. If we want to calculate height for example average of this, that is 12.5. We also have to take average of this. So for 12.5, the K2 value shall be 0.91 plus 0.97 divided by 2. Or if we will want to calculate that K2 value for 11, let's say 11, we need to linearly interpolate. Here you can see that for intermediate values at height z in a given terrain category, use linear interpolation. So what we can do here is that we can do the linear interpolation and calculate the values here. So I have done the linear interpolation and input all the values here. So Vz, that is equal to Vb into K1 into K3 into K2 into K4. So here I have multiplied Vb into K1 into K3 into K4. Here I have multiplied this value by this value, that is this formula. So we can calculate Vz. Vz is minimum for 4 meter height and Vz is maximum for 92.8 meter height. That is Vz value is 60. After that we can calculate Pz by squaring this value and multiplying by 0.6 as per this formula. After that Kd, Ka and Kc factors comes into play. Now what exactly is Kd, Ka and Kc? Kd is directionality factor, that is 0.9 for our building. Ka is averaging factor, that is dependent on the contribution area of that particular structural element. So it is 1 for a cladding. For example, if we want to calculate wind loading for the facade, then Ka's value is 1, and if we want to calculate the Ka value for RCC frames, then it shall be 0.8, and Kc value is 0.9 for our case. So if we will multiply Kd and Ka and Kc as required here, we will find that the value comes out to be 0.648, and that is less than 0.7. So code restricts us to use minimum value as 0.7 into Pz. So we have entered 0.7 value here. After that we can calculate the PD, that is Kd into K into Kc into Pz. So 1.242 into 0.7, that is 0.87. After that, in our case, there are two dimensions. One is this dimension and another is this dimension. So if we are right now considering 19.555 meter, so right now we are considering wind load along 19.555 meter, that is shorter dimension, and that is on this face. I want you to point out to this diagram. Here you will see that if force is along this direction, then this direction is called B. So if B is 19.555 meter, then this shall be the longer dimension, that is 32.25 meter. So A value is 32.25 and B value is 19.555 meter. And after that, if we will refer to this graph, here you will see that the graph is between CF and A upon B. CF is nothing but wind coefficient factor that we need to multiply to calculate the F. So F value is nothing but CF into PD into B into H. So we have calculated A upon B value and H upon B value. A upon B value is approximately 1.6, that is it lies around here, and H upon B is 4.7, that is it lies around here. So 1.6 and 4.7, we can interpolate this CF to 1.25. So we need to multiply PD into BH into 1.25, that is CF value. So we have entered CF value here, that is 1.25, and F1, that is this F value, it comes out to be approximately CF into PD into B into H. Now H is nothing but the effective height. So effective height can be calculated by averaging the upper floor height and lower floor heights. So if we right now talking about the 3.8 meter, how it comes? It comes by averaging this value, that is 4 plus 3.6 divided by 2. Or we can say the total height is 7.6, so we can say the effective height is 3.8. And here you can see that 3.6 plus 3.6 divided by 2, that comes out to be 3.6 meter. So effective area is nothing but the 19.555 into 3.6, that is we multiply B into H. B into H means this value. So CF we have entered here. So CF F1 is equal to CF into PD into B into H. CF into PD into B into H. So it comes out to be approximately 80 kilonewton, and that value has to be entered here. So we can manually enter all this data here in this window. So right now we have calculated this F value, and this F value has to be applied on the diaphragms here. So here you notice that the order is from 26 to basement 1 level. Though at basement level wind load is not applied, because wind cannot act below the ground, wind can only act above the ground. So we will apply Fx value on all these floors. And how to apply this Fx value? That we have calculated here from from bottom to top, that is from story 1 to story 26. And here I have prepared this easy file for you, that is just inverse from the value here, that is the higher, this value is written here and this value is written here from bottom to top. So we can just copy this Excel file here, press Ctrl plus C on your keyboard, or you can just right click and click on copy. Here right click and left click on paste. So this was just as easy as it is looking right now, that we just calculate all these values here and apply the wind load on the diaphragms on all these floors. And this value is not small. Here you can see that it's approximately 133 kilonewton, that is 13.3 ton applied on the center point of the diaphragm, and that is a very, I must say, large value. So left click on OK, and after that we need to apply wind load WL minus X, that is from this point. And but that we can also do that with the help of load combination, so that we don't really need to apply WL minus X. But if we want to do that, we can do that. That is not a very big concern. So WL minus X user loads, left click on. Similarly, we can put the value for wind load in the direction of minus X. Right now we have applied for wind load WL plus X. Similarly, we can do for WL minus X. We just need to write WL minus X here, type as wind, and autolator load as user loads. And then left click again on add new load, selected as a, so WL minus X is now defined as a load pattern here. After that, in the similar manner, we need to just put the minus value of this here as WL minus X. So we can just select all these cells. Please note that this is the round number of this number, so that is why this difference is coming. If we want to, so now the basically value is same. Here left click on modify lateral load and then paste all these values here. So we have now defined WL minus X also. After that, we need to define WLZ, that is wind load along positive Z direction. Or we can say that right now, so after that we need to define WLY, that is wind load along positive Y direction. So left click again on add new load. So in the similar manner with which we have calculated the wind load along plus X direction, we can have also calculated wind load along plus Y direction. So this Excel file is attached for your reference. So if you want to check or if you want to calculate all the loads again, that can be very easily calculated. So In the similar manner, as we have calculated wind load along plus x and minus x, similarly we will calculate the wind load along plus y and minus y direction. So if we will see the Excel file here, all the values are same. The only difference is that now this B, it is now 32.25 meter and this A is 19.55. So that value we have entered here. The height of the building above ground is same. So A upon B value comes out to be 0.6 and H upon B value approximately 4.7. So when we see A upon B 0.6 and H upon B 4.7, so it comes around here. So it is approximately around, CF value comes out to be approximately 1.4. So if we will input all the values here, that is story height and total height and K2, all the calculation is same except for this CF value. So CF value comes out to be 1.4 and the value that we need to enter is approximately 246 kilonewton on the top floor, and that is comparatively high as compared to this floor. Here value is approximately 13.33, but here it is approximately doubled. So we will copy all the data that is produced over here. So left click on modify lateral load, and then now this direction shall be Fy. So right click and left click on paste. Now we have copied all the data here, and then left click on OK. Similarly, we will make a wind load pattern on WL minus Y, and then left click on add new load, and then left click on modify lateral load. Now whatever values that we have generated here, it shall be multiplied by -1 to copy that for WL minus Y. So we will select all these cells and then left click on copy, or press Ctrl plus C on a keyboard, and after that just Ctrl V here, so we can copy all the data here, and then left click on OK. So now we have defined wind WLX, WLY, WL minus X and WLY. So calculating wind loads itself is somewhat a tedious process that has to be done by experienced structural engineers, especially for high-rise buildings. You cannot ignore the magnitude of wind on the top of a 100-meter building or the top of 200-meter building. Building sways a lot, so we need to calculate wind load with great precision and with great correctness, otherwise it may lead to an error. So after that, thermal load does not need to be calculated as the length of our building is less than 45 meter. Fire tender load, we don't have any non-tower area, so we don't need to calculate all these things. So we can ignore all these checklist. After that, we need to define the mass source, that we will do in the next lecture. So in this lecture, we shall define the mass source. Mass source is basically used to define the response spectrum function. So we left click on OK to close the load patterns option. After that, we go to define and mass source. Here you will see that by default some MSSRC1 is already predefined by ETABS. So we can left click on modify show mass source. We can name it as MASSSOURCE IS 1893, so that we can remember that. And after that, we will define it as specified load patterns. So we can add DL as 1. Live load we can enter 0.5, as this is an office building whose live load is approximately 4 kilonewton per meter square, that is greater than 3. So as we had read in IS 1893, for up to and less than 3, the percentage reduction is 25%, and above that, that is as our value is 4, the reduction is only 50%. So we enter the multiplier as 0.5, SIDL we need to enter as 100%, that is as 1. When we left click on OK, this option will come, that is something is wrong. So what exactly is happening? I am doing this on purpose because this is the most common mistake that new structural engineers usually do. What they do is that they double define the mass, that is they have defined the mass here also and they have defined the mass here also, and that is what ETABS is saying, that the current mass source indicate both element self mass, that is this, and at least one load pattern with the self weight multiplier greater than 0, that is DL, whose self weight pattern we have defined as 1. So it will result in double counting of self mass. So we will left click on no, and then we will untick this option, and then when we left click on OK, now it is perfectly defined. So I'm repeating here, if you are defining dead load plus live load plus SIDL here, we don't need to select here. So left click on OK and then left click again on OK. So now we have defined the mass source also. So until now we have completed up to step 9, that is we have defined the load patterns. Now we will assign the loads, that is first of all we will calculate the loads that are required as per the architectural drawings, and then we will assign those loads to our structure. If we talk about the loads that will come on our structure, now we have two plans here. So talking about loads, the loading will be somewhat different on this and will be somewhat different on this. So number one load that comes in the mind of structural engineer is the block work load or brickwork load. So here you can see that on these walls there are some block works. So considering those block works, we have to apply this block work load on our floor beams. So for example, if we talk about this wall and this wall, 1 2 3 4 5, this is a very thin block work, so we can ignore this load. This load will not matter, but this full block work height load will matter for our structure. So considering this block work, we have to calculate the UDL on our beam. I have prepared an Excel file for your easy reference. So here we can consider typical height of the beam as 750 mm, and the density of block work lies in the range of usually 10 kN per meter cube, and thickness of block work is usually 200 mm. So we can multiply, this is a simple math, we need to subtract the floor height from the beam height, because and that will be the only effective height of the block work. So in this case, for example, in floor number 5, 4 minus 0.75, that is 3.25 into 0.20, that is the thickness of block work into its density. So it comes out to be approximately 6.4 kilonewton per meter. This number is 3.25. So 6.5 is basically this equation, that is height of the block work into its thickness into its density. This UDL we have to apply on our floor beams. We can go for all story option and we can apply brickwork load on all these beams. 1 2 3 4 and 5. 3 4 and 5. 6 7 8 9 and 10. 6 7 8 9 and 10. So total 200 frames are selected. So we just need to assign frame loads distributed. Please note that brickwork loads comes under the SIDL loading, that is superimposed dead load. We can assign the value of 6.5 kilonewton per meter. Direction is gravity, it is a force, not a moment. The load pattern name is SIDL, and we can either go for add to existing load or replace existing load, it will not matter. So left click on apply. So 6.5 kilonewton per meter load is applied on all the floor beams. We can check that with the help of 3D view. So you can see that on all the floors this loading is applied, and on the upper floor this projection is not there. So on all those floors this projection loading is not applied. And after that we it is a best practice to apply the loading of this fixed glaze window also. So we can apply 500 kg per meter or 5 kg per meter loading on these beams. So we can select these beams here, that is this beam and this beam, and we can apply loading of 5 kN per meter. So here you can see that this loading is now applied on these beams and these beams. So after that if we will talk about this glazing, so we also need to apply this load on our model. So what we need to do is that we need to individually select all the beams. So we can go for display. Please note that if loading value is given, the all story and one story option will not come here. So we need to go for display undeformed shape. Only then this option will come. So we can select all these beams. So we have considered the value of 5 kN per meter for the glazing load, SIDL, and then left click on apply. Total 30 frames are selected, that is on 15 floors. So we can see that this loading is now applied on all the floors. Now we have applied this loading also, that is superimposed dead load block work loading. After that we need to apply the staircase loading.
So, students, we'll stop over here. We have discussed up to the application of the loads, and then next class we'll discuss about how to. Next part I'll discuss how to, what you call, proceed with the